Let me thanks for organizers for having me here. My name is Nurlan Yerkinbayev. I am PhD student from Kazakhstan, and my supervisor is Professor Plemelj Nazarboy Kadyrovich. So today I would like to talk about boundary conjugation problems for piecewise analytic functions in Besov spaces. Let's introduce the definition of boundary conjugation problems. Here, let gamma is simple closed contour, and here nu satisfies this inequality, and the gamma is dividing the complex plane into the domains d plus internal and d minus external, which including infinity point. And it's required to find the analytic function phi, big phi, that belongs to Besov space, which embedded space of continuous functions. And on the gamma, the following relations are following the satisfying. Here, second, okay. Here, first is homogeneous problem, and the second is inhomogeneous problem. Where these functions belongs to Besov space. And here big phi plus z is analytic function when z belongs to d plus. Respectively, big phi minus z analytic function when z belongs to d minus. Okay, let phi function belongs to Besov space, and phi satisfy this inequality, and then the Cauchy type integral exists, which belongs to Besov space. And here this integral belongs to Besov space. It's proved this book, which written by Professor Plemelj. Under our conditions, the following formula holds. Here phi plus and phi minus are analytic functions, and then there exists singular integral operator here. Then the following Sokhotskii, it's a famous formula. Sokhotskii-Plemelj formulas are valid. These follow from the results this articles and book articles. Then theorem. First, there are G here kappa is index of function, and p kappa is a polynomial of degree kappa. Then theorem, if kappa non-negative, then the homogeneous problem has kappa plus 1 linearly independent solutions, and it defined by these formulas. The general solutions are determined by these formulas, where where pz equals to this integral. And if kappa negative, then problem 1, which homogeneous problem, is unsolvable. And then a second theorem: if kappa non-zero, non-negative, problem 2, which inhomogeneous problem solvable, and its general solution is given by this formula, where canonical function xz is determined by this formula. And here, if kappa equal to -1, then the problem inhomogeneous problem is also solvable and has a unique solution. Then in the case kappa less than -1, the problem 2 is unsolvable. In order it to be solvable, it's necessary and sufficient that the free term of the problem satisfies to the conditions, this condition. Then the unique solution of inhomogeneous problem is given by formula 10, like this, where p kappa z equal to 0. And when we studied this problem, we used famous method of book which written by Gachov and Muskulishvili. Then this problem solved in Elpis spaces and Holder spaces, but not Besov spaces. So thank you for your attention.
If no questions, then let us thank the speaker again.